Hello and welcome. I want to show you one more sorting algorithm, and that is Quicksort. So Quicksort is simple, it's fast, and it's fun. So we're talking about sorting. As a reminder, we have a sequence of numbers and we want to find the permutation of that number, so the reordering of those numbers such that we have them in an increasing sequence. Two properties of sorting algorithms that we've been looking at is a running time, and that is a running time in the worst case, and whether it's in place or not. So whether we have to allocate extra memory to move the numbers to, and so on. Two sorting algorithms that we've seen are insertion sort and merge sort. So insertion sort, what was the running time? Running time is n squared, and it was in place. Then merge sort, the running time was n log n, and it was not in place. And now we're going to see Quicksort. Now, Quicksort has a worst case running time of n squared, but we'll have to say more about that in a moment. It is in place, but that seems that we don't really gain anything by having Quicksort. That is wrong. Quicksort is faster than it seems to be. So why would we want to do Quicksort? Because on average, and now we are going to see an example of a randomized algorithm, randomized Quicksort, on average, so in expectation, it's actually very fast. So the expected running time is order n log n, and order n log n can mean many things, but those constants for Quicksort are also small. So it's a fast, in expectation, n log n time algorithm. So my plan here is the following. I want to show you Quicksort. I want to give you some intuition of why on expectation it runs in order n log n time. We are not going to do any type of formal analysis of Quicksort. So what is Quicksort? Quicksort is a divide and conquer algorithm, just like merge sort. So we have a divide step, we conquer, so we go to subproblems, and we combine. So that is generally how divide and conquer works. But for merge sort, what we had that was at the dividing, in the dividing step, we didn't really do any work except for copying. And then all the hard work we did when combining. Now for Quicksort, it's the other way around. We do the work when we divide, but then in the combine step, we don't need to do anything anymore. When dividing, what we do is we're going to partition the numbers. More specifically, we're going to look at a specific entry A of q, and we're going to subdivide the array into numbers smaller than A of q and larger than A of q. Of course, since they're not sorted, we will first have to rearrange numbers such that everything smaller than A of q is at the beginning of the array and everything larger at the end, and then we can split. So that's the idea of partition. So Quicksort essentially partitions the array and then recurses. So that's how it looks like in short. As long as there are elements left, we do the following. We partition A into two parts. This will give us an index q at the end, which is the index at which we want to split. And then we call recursively Quicksort on the first half, not half, on the first part, and on the second part. And the initial call will be for the whole array, so that will be with 0 and n minus 1. What does partition do? Partition needs something that is called a pivot. The pivot is the element which we use to divide the array, as in saying everything that is smaller equal goes on in the one part, everything that is larger in the other one. So what we're going to do here is, as pivot, we're going to select the very last element in our range. The range goes from P to R, so the last one is AR. So the idea of partition is the following. We take the last element, AR, as the pivot. So that's the element that we have here. Now I will point at P minus 1, so I will actually point here, and J will start at P. So J starts here. We have two indices. What these indices will do is they will mark the part that is smaller equal x, so smaller equal up pivot, and the part that is larger than x. Up to index I will have all the elements that I've seen so far, which are smaller equal x, and then I will have the elements larger than x up to j. So how does this work? So you imagine we're in this loop with j. So the next element that we're going to look at is the following. The element here. Now, what we're going to do is we're going to compare it to our pivot. So if it is smaller equal x, it should be in this blue part here. So how can we get it into the blue part? Okay, we can want to place it here. There is a different element there, but that element should be in the green part anyway. So if I move this here, I'm fine. So then I've moved the green part by 1 and added that last element to the blue part. If, in contrast, this element is larger than x, then I can simply move this boundary, so this j by 1. So that's how partition works. And the loop invariant for partition corresponds exactly to that. It says all elements up to I should be smaller equal to pivot. All elements between I plus 1 and j should be larger than the pivot. And then at the very end, this is a pivot because we picked that one as a pivot. Okay, let's do this by an example. If this is my input, so 5 is my pivot, what do? I compare my first element to 5. It is larger. What does that mean? I'm going to move j, but I'm not going to move I. So, which means 8 is now in my green part, the blue part is still empty. Next, I'm going to look at the 1. The 1 is smaller than 5. What do? I swap 1 and 8, and I move both I and j. I mean, j I always move. I mean, it's a loop over j. J always moves. The question is, does I move or not? And I moves if I find something that has to go into the blue area, and that is the case here. So 6 is larger than 5, so I do nothing except that j increases. 4 is smaller than 5, so what do? I exchange 4 and 8, and also increase I by 1. And that is what we get. And then in the next step, I have the 0. 0 is smaller than 5, so I'm going to swap 0 and 6, and we get this. Now I'm here, 3 is smaller than 5, so I swap the first element in the green one, that's 8 and 3. I also move I by 1, j moves by 1 anyway. I'm here. Last iteration of my loop, I have a 9 here. 9 is larger than 5, so I don't need to do anything except that j moves. And this is what I have now at the end of my loop. And the loop is here, these lines. Now I'm done except that 5 is at the end and it shouldn't be there. 5 should actually be, you could say, in the blue part. How do I get 5 there? Easy. I do what I did previously with elements that were smaller than 5. I'm going to swap 5 and 6. And now I have exactly the structure that I want to have. I'm going to return I plus 1. What does that mean for us? It means that then the quicksort will recursively work on green and on blue. Again, for blue picking a pivot, that would be 3 in this case. Find everything smaller equal 3 and then everything larger than 3 and recurse. Likewise on green. So this is partition and how it would be used in quicksort. Let's prove the loop invariant. So the loop invariant was essentially that in blue, so up to I, we have elements smaller equal x. In green, so up to between I and j, we have elements larger than x, and at the end we have x. So initially, I is p minus 1, and j is p. So in this case, the arrays that we're looking at are empty. Yeah, so I have the array from p to p minus 1 plus 1, from p to p, not including p, so that is empty. And I have the array from p plus 1 to from p minus 1 plus 1, so that's p up to p, also empty. So initially, both blue and green are empty. X, so the pivot is at the end, so that's also fine. All three of these hold. Maintenance. Maintenance, we have a case distinction because we have a if statement here. And in both cases, we can check that, again, blue and green are maintained correctly. So the simpler case being that if the element is larger anyway, then x, simply adding it to the green part is fine. If it is smaller, then by swapping it with the first green one and moving I by 1, then this element, because I just swapped it there, I know it is correctly if it's in the range up to I. While this one, because it was previously, I know that it was larger than x. So having it here and then moving j to here still gives me something that should be in the green area and is in the green area. So I am fine. Termination now just gives me, if I put all of this together, it gives me that at the end of the loop, I have this structure, and that means I have first element smaller equal, then the elements larger, and that is exactly what I wanted to have. And then if I swap in this element here, then indeed I have the smaller equal elements to the left and the larger elements to the right. So what is the running time of this algorithm? It depends on the size of the subarray, so how many elements I have between P and R. And let's make this a quiz. So what is the running time of partition on a subarray with n elements? So is it log n, n log n, or n squared? It is of order n, and the reason simply being that I loop here over. So I'm doing this n times, and whatever I'm doing in the loop is actually constant. Constant type n, order n. So that is partition. And now partition is a key ingredient to Quicksort. So let's now go from partition to Quicksort. Here once more is what Quicksort does, and actually it doesn't really do anything except for partition plus recursion. The running time of Quicksort obviously depends on how do we do the partitioning. Let's assume we would always partition in the middle. Yeah, so somehow by luck or chance, I have this array, I have my pivot here, and for some miraculous reason, this actually fits exactly here, and we have smaller equal x here, larger x there. So if we get a balanced split, then the running time would be T of n is T of n half to solve for this recursive call, T of n half for that recursive call, plus partition to linear time. This exactly corresponds to the merge sort recurrence. But this is only if our partition ends up in something nicely balanced. If it's unbalanced, then we're in trouble. I mean, imagine x is not here, but imagine all elements are smaller equal x. Then actually we do all of this work of partitioning without making any progress. I mean, a tiny bit of progress, because we now know that x is at the end. But then n minus 1 elements remain, we do the same again, and in the worst case, we after that have n minus 2 elements, n minus 3 elements, and so on. Every time spending linear time, this will give us quadratic time. So if one sub-array is empty and n minus 1 element in the other one, we get a running time of, so this is t of n is t of n minus 1 plus, okay, t of 0, so this one you can ignore, plus theta of n. And this would solve to n squared. So that's the worst case. The best case is this merge sort case, or the balanced split case. There we get this recurrence t of n is 2 times t of n half plus theta of n. And it would nicely solve to n log n. So what does the average case give us? For that, we first have to say, what do we mean by average case? I mean, why are we allowed to take an average here? So the idea of doing an average case here is, let's assume that instead of simply taking the element that is at the end, we swap a random element to the end. And then do the partition. This means that any element in my sub-array has the same probability of being the pivot. So, and under that assumption, we can talk about average case. And what we're going to see is that the average case is actually much closer to the best case than it is to the worst case. And why is that? So what is the intuition behind this? So intuition is the following. So imagine the partition would always produce a 9-to-1 split. Yeah, so imagine we have, this is our array, and 9-to-1 would be that, let's say this is 1 unit, this is maybe 9 units. Let's say we always split like this. This already looks like a bad case. I mean, you would hope that most of the splits are actually with something closer to the middle if I picked a random element. But even in this really bad case, if I look at the recurrence, so what would the recurrence be? It would be t of 9n divided by 10 plus t of n divided by 10 plus theta of n. Now, how do we solve this recurrence? We cannot use the master theorem because these two terms are different. So it's not 2 times something. We can use recursion trees. Let me show you the corresponding recursion tree. So top level n. So this is recursion trees as we know them. Top level, we have the n here. Then we have 2 branches because we have 2 t's here. One is for 9n divided by 10. One is for n divided by 10. So here we have the one for n divided by 10. There I get n divided by 10, and it again has 2 branches. One corresponds to this divided by 10, so it's n divided by 100. The other one corresponds to the 9 times this divided by 10, so 9 divided by 100 times n. Same here, the other branch. So I have the 1 divided by 10 n branch and the 9 divided by 10 n branch. The 9 divided by 10 n branch has again 2 branches. One corresponds to 1 divided by 10 times this number, so that is 9 divided by 100 times n. And the other one is 9 times this, so 81 divided by 100 times n. If you look at what we get here, at least at the top levels, it's again always adds up to n. So contribution per level is n, 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 and so on. Now, what is the depth? And that is now a bit of the tricky part here. The depth is not uniform, meaning that here, where I keep more of the n, the tree will be much deeper than here, where the depth is essentially log n base 10. So the depth varies between log n base 10 and log n base 10 divided by 9. That will be somewhere here. But no matter, so also on those lower levels, we can always bound the sum over on that level by n. I mean, there will be parts missing here, so it might be less, but it's still not more than n. So then we get, as an upper bound, n times the number of levels. The number of levels is, as always, because we have a log of n to some base, and the base is constant, is of order log n. So overall we get n times log n order n log n. Some levels are full, some are empty, but and the base of the log is kind of, unusual. So we have here base 10 and here we have base 10 divided by 9, but that doesn't matter for up to constants. So the running time, if we would have these splits, would be n log n. So if we have nicer splits, so back to our example, this was a split somewhere here, let's say, or somewhere here. Now we could have a split somewhere here or here. All of the nicer splits actually give us even nicer running times. So as long as I do my partition with something that splits the area into 2 halves, and the 2 halves, and it splits somewhere in here, I'm perfectly fine, and I would get this n log n. So as long as I can kind of split off a constant of the original part, I'm perfectly fine. But of course we could have really, really, really bad splits. So maybe something here. I mean, it's probability, it can happen. It can happen, but it is unlikely. And even if we have bad splits, we'll always have enough good splits so that we make enough progress. So let me give you a bit more intuition about this. So let's assume we have some kind of mix of good and bad splits. So what we can expect is that because it's very unlikely that we split off a very small part, we will have more good than bad splits. I mean, in expectation, we have to be a bit careful here in terms of formal analysis. So let's assume a somewhat bad case where actually every second time we have a bad split. So how does a bad split look like? Let's say this is kind of the worst possible setting where I'm not splitting off anything except for my pivot itself. So I go from n to n minus 1. This is a really bad split. And then a good split is, let's say, roughly splitting in 2 halves. Now, if we would alternate between those two, actually what would happen is that we would get kind of twice the number of levels, but essentially if I compress 2 levels, I'm again going from n to n half and n half. Meaning I kind of expect that the number of levels goes up by some kind of constant, but otherwise I should be making progress as much as I would be doing if I always have nice splits. And that gives me overall n log n. So this is very much on the intuitive level. And of course, if you would really want to know this, you should read up on Quicksort and look at the formal analysis. Okay, but I hope this gives you some intuition of why Quicksort is fast in expectation. And fast in expectation again means we're using randomization. So we're looking at randomized Quicksort. So we pick a pivot at random that would look like this. So first of all, we take a random number between P and R. We use this to swap a random element to position R, and then we call partition as before. And because we get reasonably nice splits, we get an expected running time of theta of n log n. We didn't prove that here, but you can look at any textbook to get a formal analysis like the Corman et al. Book. So much about Quicksort. Quicksort is a fast and simple algorithm. In particular, it's also fast in practice. So I wanted to say a few more words about sorting fast in practice. In particular, because we like to use Python. How does Python actually sort numbers if you ask it to do so? So that depends on your Python implementation, but if you use CPython, what actually happens in the background is something that's called Timsort, and that is not a misspelling of time, but it's somebody called Tim who invented this algorithm, and it is a hybrid sorting algorithm. So what does that mean? It means that it mixes 2 sorting algorithms, and the 2 sorting algorithms that it mixes is merge sort and insertion sort. So it does merge sort on a very general terms. It does merge sort down to a certain size. And if you only have sub-arrays of a certain size left, then it does insertion sort. Actually, in C++, there's something similar where instead of merge sort, you're using quicksort. But in Python, it's merge sort plus insertion sort. And the size is actually not a fixed size, but it's somewhere, let's say, between 32 and 64. And I'm saying it's not a fixed size because in this algorithm, there are more tricks to make it fast in practice, and I would just want to briefly touch upon them. So one is that we're actually not fixing the size of where we move to insertion sort. And the reason being, insertion sort obviously works brilliantly if the array is already sorted, because it simply just runs through it. It doesn't have to do anything. Now, in real life data, you often have already partially sorted data. So it's not unlikely that you actually see something or see parts of your data that are already sorted. So then those parts, ideally, you just don't want to touch. So insertion sort is perfect for it. And that's why while you're trying to do insertion sort on smaller parts and you see, oh, I could actually go further without extra cost because it's already sorted, then you do so. And that's why we get this variable size. Also, given that in practice, you often have parts of your data that are already sorted, you of course also want to take into account that those parts might be actually decreasingly sorted. So if you do insertion sort on a decreasingly sorted sequence, that's actually kind of the worst case setting for insertion sort. But it's easy to fix if you kind of observe and make sure that if you see something that is decreasingly sorted, simply reverse it and you're fine again. Some other tricks that I used is it uses not insertion sort as we've seen it, but something that is called binary insertion sort, which means that if I have a new element, which I have to kind of put into my already existing elements, so what the simple insertion sort does, it starts at the end, compares, and shifts everything to fit. Okay, the shifting we cannot avoid, but all of these comparisons we can avoid by doing a binary search on these. So we do binary search with know where to insert and then shift. So that's binary insertion sort. That's also used in Timsort. And then there are more tricks concerning the merging of merge sort. So if you think of the merging, you have two runs that you want to merge. You look at the smallest number in both runs. You take the smaller one, put it at the beginning, then take for that one the next smallest, and so on. Now, what we want to use here is that often enough you have a setting where, let's say, in the one run you have numbers somewhere 2, 3, 6, 8, 9, 11. This is my one. The other one is maybe 0, 100, 500, and so on. So often enough we might have data where we have lots of close by numbers in one of my runs. Now, instead of pointing here and doing always pairwise comparisons, what we can do is when we have the 100 here and we've moved here for a while and have seen that this 100 is simply not coming, so we're taking many elements from here, what we can do is, instead of always comparing the numbers that we have here to 100, actually we do a binary search for 100 in here, or something like a binary search. And then if we know where the 100 fits here, which would be here at the very end, then without comparisons, I can simply move everything here into my merged array. Okay, so that's Timsort, just in case you were wondering what Python is doing. So this video was about Quicksort. We saw that in the worst case, it's quadratic time, but randomized Quicksort in expectation is order n log n time, and it's also fast in terms of the constant. And generally speaking, if we want to do fast sorting in practice, hybrid sorting algorithms are good, like merge sort with insertion sort, or also quicksort with insertion sort. Those work nicely. To wrap up, one last quiz. if we don't use randomization, what is a worst case input for Quicksort? Is it if the input already is sorted? Is it if it is, okay, we don't have randomization, but as random as possible? Is it actually difficult to construct? Or maybe there is actually no worst case input in the sense that we cannot get quadratic running time. The correct answer here is if it's already sorted. So if it's already sorted and we don't do any randomization, then the pivot that we're picking will be the last element. So we're not doing, the partition will not split anything. Everything is smaller equal my pivot. And that continues further because the next time I want to partition, I use a second largest, the third largest, and so on. So I can indeed get quadratic running time in that setting. So randomization is a good idea. There are also alternatives to randomization. So there are ways to pick pivots deterministically if we want to, but that is fairly expensive in terms of a constant. There's also ways to kind of make sure that the randomization more often ends up in something balanced by, for instance, taking three numbers, three random numbers, taking the middle number of those and take that one to partition. So there's still much more to say about Quicksort, but this is what I wanted to say. See you next time.